Limits and continuity. The limit as xy goes to ab of f of xy equals a value L if, for any epsilon greater than 0, there exists a delta greater than 0 such that if xy is in the domain and 0 is less than the square root of x minus a squared plus y minus b squared, which is less than delta, then the absolute value of f of xy minus L is less than epsilon. Now, what does any of that mean? So I have a picture here. I want to help you with the understanding. You might have to take a little time to think about it. But notice that this piece right here is a circle, right? It's a circle centered at a comma b that has a radius no bigger than delta. And if you've never dealt with delta and epsilon proofs before, when we say delta and epsilon are greater than 0, in our heads, because what really matters, is that delta and epsilon are shrinking down to 0. Because it's easy for things to be true when you have really big radii or really big delta epsilons. But it's harder for things to be true when these things, delta and epsilon, shrink down to 0. So this part again, x minus a squared plus y minus b squared, is a circle. We take the square root. That's a distance. And really what we're talking about is the distance of all points that are no more than delta away from a center AB. So that's what this part of the picture down here is representing. And so what we really think about is as this circle is shrinking around AB, you know, AB maps to a point up here, or maybe there's no value, like we could have like an open circle like we would do in two-dimensional, if it helps you think about that. But as this circle shrinks, does this distance epsilon also shrink on both sides? Or does it squeeze towards our limit? So as the circle shrinks, does this distance of all the points that are mapping into the circle, all the points in the circle mapping to our function z equals f of xy, do all those values shrink towards this limit? That is, does this distance away from the limit, epsilon, go to 0? Now, that's the understanding. But if you really want to understand that, I recommend drawing some pictures, maybe drawing some counterexamples. But that's not really the point of this video, because the precise definition of the limit is only needed to show when a limit exists. If you recall from single variable calculus, the limit exists, the limit as x goes to a of f exists, if and only if the limit from the left side equals the limit from the right side. That is, there are two paths we can go down towards x equals a, and y needs to be going towards the same value from both sides, or from both paths. In multivariable calculus, all paths, every single possible path towards a point, must give the same limit. So if we want to do an example where I know that the limit does not exist, let me show you an approach that I could take. And I have pretty standard things that I try, but sometimes when things get complicated, you might have to figure out different paths. However, what I'm trying to do here, and I'm going to draw the xy plane, and you imagine the z plane is coming out of the board. And so I need to go towards 0, 0. That is, xy needs to approach 0, 0 from every single path, and I must reach the exact same value. So what I do, especially if I know or don't think that the limit exists, I'll start choosing paths. So path 1 is, let's go down the positive x-axis. towards the origin. This is a pretty standard path that I try. So maybe I have values of xy that I'm plugging in, and then I'm going this way towards the origin. Notice that if I'm going down the positive x-axis, y always equals 0. So if I use this fact that y equals 0, and I want to find the limit as xy goes to 0, 0, and it's really as x0 goes to 0, 0, I have x squared minus 0 squared over x squared plus 0 squared, which equals 1, because we get x squared over x squared. And remember, x doesn't quite equal 0. Limit is when we get really close. Let's try another path. Let's do another simple path, and let's go down the positive y-axis. And so maybe I'm starting up here with some values, and I'm going down this way, down the positive y-axis, where x equals 0. So we're finding the limit as 0 comma y goes to 0, 0. And if I plug in, I get 0 squared minus y squared over 0 squared plus y squared, which equals negative 1. So notice that when I went down two different paths, I got two different limits. One clearly does not equal negative 1, which means the limit does not exist. Let's take a look at another example. F of xy equals xy over x squared plus y squared. Now I'm asking you, does the limit exist or not? So once again, I'm going to draw xy axis and imagine the z coming out of the screen. And we're going to go towards the origin. And I'll do the same two paths. Let's do path 1, where y equals 0. So we're going down the positive x-axis like that. And if I plug in y equals 0 into my limit, so we'll do the limit as x0 goes to 0, 0 of our function, we're going to get 0 over x squared, which is 0. Same path 2. We're going to let x equal 0, so we're going down the positive y-axis in this case to be a little more specific. So the limit as 0y goes to 0, 0 of f of xy equals, if I plug in 0 for x, I still get 0 on top. And now I get y squared at the bottom, but it still equals 0. Does that mean the limit exists? Well, two different paths give the same limit. That must mean the limit exists, of course, right? Well, no. Because there are an infinite number of paths that I could take to get to 0, 0. I could do this one if I wanted to. Or something over here, maybe a little simpler. Or how about this one? Let's go down the line y equals x. So for path 3, we're going to try the line y equals x. So this is the limit of x comma y, but y equals x, right? So x comma x goes to 0, 0 of our function. Again, it's xy, but y equals x, so I can say x comma x. So the limit, if we plug in back up into here, is going to give us x squared over x squared plus x squared, because y equals x, which equals 1/2. So since we have a path whose limit does not equal other paths, we know that the limit does not exist. Okay, so let's look at one where the limit does exist. And I'm just going to tell you, I know it exists. I even know what the limit equals. Let's say the limit as xy goes to 0, 0, 3x squared y over x squared plus y squared equals 0. So we have to use our definition. So I'm going to write part of it back here for us. So if 0 is less than the square root of x minus 0 squared plus y minus 0 squared is less than delta, then for the limit to exist, my function, 3x squared y over x squared plus y squared minus 0 must be less than epsilon. I think the best way to think about this is the following. As delta goes to 0, does this thing, 3x squared y over x squared plus y squared minus 0, also go to 0? That's what we're going to try to show. So let's take a look at 3x squared y over x squared plus y squared minus 0, but I don't need to write the minus 0, right? I can rewrite this as 3 times the absolute value of y times x squared over x squared plus y squared. I don't need absolute values around the squared parts because they're already positive just by their nature. Now, what else can I say here? Well, I can say this is less than or equal to 3 times the absolute value of y. Now, why am I allowed to say that? Well, I know that x squared plus y squared must be greater than or equal to x squared. Because y squared is a positive value, which means that x squared over x squared plus y squared must be less than or equal to 1. Which allows me to make that statement. Now, I could rewrite this part over here as 3 times the square root of y squared. The square root of y squared is technically the absolute value of y. Let me circle this. This is what I use to show this part. And then I do a little bit of algebra again. So let's take this part over here. I'm going to bring it back down over here. 3 times the square root of y squared. And notice that this is less than or equal to 3 times the square root of x squared plus y squared. Because, of course, x squared is positive or 0. So x squared plus y squared must be greater than y squared. But notice now that this is less than 3 delta because of my statement right up here. We're assuming, that's part of the assumption we're allowed to make, that the square root of x squared plus y squared is less than delta. So here's what we do. It's sometimes confusing, takes a while to kind of understand it. But we're going to let delta equal epsilon over 3. Notice that we get three x squared y over x squared plus y squared, which is all the way, if you follow the inequality signs all the way down, is going to be less than delta times 3, but delta is epsilon over 3. And technically, we've shown what we needed to show. To explain just a little bit more, what we've done here is saying for any epsilon greater than 0, we can find a delta greater than 0 such that, ST is such that, the square root of x squared plus y squared less than delta implies f of xy minus 0 is less than epsilon. There is a formal delta epsilon proof with a 2-variable input. But let's do continuity just really quickly, because if you understand limits, you'll understand continuity. So the definition of continuity we're going to use is f of xy is continuous at a point AB if the limit as xy goes to AB of f of xy equals the actual function value at AB. So let's show that f of xy, defined piecewise as 3x squared y over x squared plus y squared when xy does not equal 0, 0, and defined at 0 as xy equals 0, 0, show that this function is continuous at the point 0, 0. Well, from the previous example, we already showed that the limit as xy goes to 0, 0 of 3x squared y over x squared plus y squared equals 0. We define f of 0, 0 to equal 0. So by definition, we have shown that the function is continuous at the point 0, 0.